In this video, we talk about floating point representation. We know that the psi magnitude, one complement and two complement representations that we have just presented deal with psi integer value only. However, without any modification, the format are not useful in scientific or business application that deal with a real numbers values. So basically, the number including both of the integer and also the fractional part as well. Floating point representation solve this problem for us. And if we are a skilled programmer, we can perform floating point calculation using any integer format. This is called a floating point emulation because floating point values aren't stored as hash, and we just create a program that make it seem as if floating point value are being used. However, most of today's computers are equipped with specialized hardware that perform floating point arithmetic with no special programming required. So we don't have to write or create a program in order to do the floating point representation. So floating point numbers allow an arbitrary number of decimal places to be to place to the right of the decimal point. So for example, we can have 0.5, just one number behind the decimal point, time with the 0.25, so that two uh, digit after the decimal point, and we multiply with each other, we can get another one 0.125, so three digits after the decimal point. They are often expressed in a scientific notation. So for example, 0.125 can be represented by 1.25 times 10 power negative 1, or 5 million equal 5.0 times 10 power 6. Okay. Computers use a form of scientific notation for floating point representation. So basically, number written in scientific notation have three components. The first part right here just represents the psi. The second part right here just we call a mantissa, and the last part we call exponent. We can explain detail of each component in a few seconds. Computer representation of a floating point number consists of three fixed psi fields. So the first field right here to represent the psi of the number, the second field right here to represent the exponent of the number, and the last field right here to represent the significance of the number. So this is a standard arrangement of the fields, and also we should note that the significant and mantissa do not technically mean the same. Many people use them interchangeably, but we use the term significant to refer the fractional part of the floating point number we will represent in this video and in this course. So the size of the floating point representation, that's a 1-bit size field, and to store the value of the size of the number. So basically, if the number with the value of 0 positive, we have the size equals 0, and if the number is a negative, we have the size equals 1. The size of the exponent field determines the range of the value that can be represented. So basically, this is a larger size, we can represent a larger number. The size of the significant determine the precision of the representation. So this part right here basically represent the fractional part of the real number. So we introduce a hypothetical simple model to explain the concept we just discussed so far. So basically, in this model, we have the floating point number is 14 bits in length. The exponent field is the 5-bit and the significant field is the 8-bit. So we have the 8-bit here, 5-bit here, and 1-bit here. So the total we have the 14 bits to represent the number. So this model we have the 14-bit floating point model. Also, we notice that the significant is always preceded by an implied binary point. So the vertical line right here is just imagine just a binary point right here. Okay, so that the significant always contain a fractional binary value. So all the number represented in here represent the fractional part of the binary representation. And the exponent indicate the power of 2 by which the significant is multiplied. Okay, so this part right here represent the exponent of the with the power 2 that this part can multiply with. Okay, and this one the size just represents the size of the number. We can show through example. So here the simple example to show how the floating point can be used to represent a number. So for example, we have the number 32 in decimal, and we want to use the simplified 14-bit floating point model to represent the number 32. Okay, so first of all, we know that 32 is the 2 power 5. So in binary scientific notation, we can represent 32 equal to 1.0. So basically, is this 1 times 2 power 5. Okay, so times 2 power 5 got the 32. So 1 times 32 equal to 32. And also we can we can see that actually this representation can also be represented by 0.1. So we shift one the decimal point right here to the left. So we have the one more 2 right here. So 0.1 times with 2 and times with 2 power 5, so equal to 0.1 times 2 power 6. And later on, just a moment, we will explain why we prefer this kind of a representation than the first representation here. Despite they are represent the same number, but we gonna prefer this one, capital standard one. Okay. So using this information, we will put 1, 1, 0. So that's a binary representation of the value 6. That's the exponent value right here in the exponent field. Okay, so basically 1, 1, 0 going to be 1, 1, 0. And the remaining bit right here is just insert a part 0 in. And the significant that's right here, that's represent we have the point right here, and the value or the digit right after the binary point right here is just 1, and then the remaining bit just 0 with just part 0 in. So the number 32 in decimal can be represented by a 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0 in a 14-bit floating point model. Okay. So as we shown before, there's a many way to or equivalent way to representation of value 32 using the simplified model. So for example, we can have the 2 power. This is 2 power. This is 2 power 6. This is 2 power 6 times with 0.1. Also, we can represent 32 by 2 power 7 times 0.01. Also can be represented by a 2 power 8 times 0.001, and also can be represented by 2 power 9 times 0.0001. Okay, so all of them are equivalent. That's all of them represent the value of 32 in decimal. So with this different way to represent a number, just not only waste the space, but also can cause the confusion. Okay. Also, another problem with our system is that we have made no allowance for a negative exponent. So, for example, we have no way to express the value of 0.5 that's equal to 2 power negative 1. And we should notice that there's no sign in the exponent field in order to represent this scenario. So all these problems can be fixed with no change to our basic model with some additional rules. So basically, to solve the problem of synonymous form, we establish a rule that the first digit of the significand must be equal to 1. Okay, so it means the digit right after the binary point should be have the value of 1, and with no 1 to the left of the radius point. Okay, so that's the first rule. This process called a normalization and result in a unit pattern of each floating point number. So basically, in our simple model, all the significand must have the same form 0.1 something, where x right there can be 0 or 1. Okay, but the first two digits need to be in this form 0.1. That's a normalization form. For example, if we have the number 4.5, so 4.5 basically 4 can be represented by 1, 0, 0, and 0.5 can be represented by 0.1. So basically this equals this gonna be the same with time 2 power 0, because 2 power 0 equal to 1. So this one just a number representation of 4.5 in a binary. Okay, so this one also equivalent to 1.001 times 2 power 2, because we move the binary point to into two spot. So we're gonna have the move the binary point from here to here, so we have the 2 power 2 right here. We also can move one more spot right here. We get 0.0.1001. That's this value right here, and then we're gonna increase the exponent by 1. Okay, so we have the last value times 2 power 3. So the last experiment, that's the correctly normalized, and we're gonna use this representation to for the floating point representation. Okay. So to provide the negative exponent representation, we will use a bias exponent. Okay, so basically in our case we have a 5-bit exponent. So the bias number will be computed by 2 power 5 subtract 1 and subtract 1. So that's basically equal to 2 power 4 subtract 1 equal to 15. So that's a bias number of the exponent. Okay, so just we use 15 for our bias, so our exponent will use the we call the excess 15 to represent the exponent. Okay, so in our model, exponent value less than 15 are negative and representing fractional numbers. So let's consider a example of representing value 32 in decimal, and we use the revised 14-bit floating point model. Revised here is mean now we use the excess 15 to represent the exponent, and we also use the normalization to represent the the other part of the floating point number. Okay, so basically we know that 32 equal to 1.0 times 2 power 5. Okay, so that's the same as before, but now instead of using this form, we're gonna normalize, so we need to have the form of 0.1. Okay, so when we move the binary point from this position to this position, so we need to increase the exponent by 1, so we have the 2 power 6 instead of 2 power 5, because the binary point have moved from here to here. Okay, so basically we have the 32 equal to 0.1 times 2 power 6. So this is in the normalization form. Okay, now in order to represent the exponent value right here, we use the XS15 bias exponent. Okay, so basically we just take the value of the exponent right here and we add 15 to it. So 15 and we add 6, so we get a 21, and then we're gonna transform the 21 into binary representation. Okay, so that's the exponent part of the number 32. So the number 32 will be represented using floating point representation as follow. So we have this is the positive number, so we have the 0 for the sign, and the we use the excess 15 for the for the exponent. So this one gonna be represented in the exponent right here. Okay, and the last part right here, that the significance. So we can see that the point the binary point right here. So right after binary point, we have the 1 right here. So and the remaining just 0, because this the there's no value after the digit 1. Okay, so we put all 0 after 1. So now another example. For example, now we want to represent the number 0.0625 in decimal using the revised 14-bit floating point model. Okay, so the first step is that we're gonna transform this decimal number into binary representation. So we knowing that using the methods of Bayes conversion, as we discussed in the previous videos, we can see that this decimal value actually can be represented in binary by 2 power negative 4. Okay, so we this one not in the normalization form, so we need to transform into the normalization form. So basically we put 0.0625 1.0 times 2 power negative 4. So transform into the normalization form. We're gonna move the binary point 1 spot right here, and we get 0.1, and then we have the 2 times 2 power negative 4, so that we get the 2 power negative 3. Okay, so to use our XS15 bias exponent, so we take negative 3 add to 15, and then we obtain 12, and we gonna represent 12 in binary by and we get this binary string. So this binary string gonna be put into the exponent part of the model. This number right here, that's a positive number, so the sign equals 0, and the remaining right here, that's the after the binary point right here, that's a 1, so 1 gonna be here, and the remaining part gonna be 0. Another example, for example, we want to represent a negative 26.625 in decimal using the revised 14-bit floating point model. So first of all, we're gonna represent the positive value of this number, that's the 26.625 in binary. So the first part right here, 26, gonna be converted into this binary string, and the fractional part right here gonna be represented by this binary string. Okay, so we have the binary point right here. And we knowing that this one is not a normalization form yet, so we need to normalizing and in order to doing that, we're gonna shift the binary point from here to all the way up here. Okay, so we have 1, 2, 3, 4, 5. So that's this number gonna be equal to this number times 2 power 5. Okay, 5 because we move the binary point in to the left hand side 5 spot. Okay. Also, we know that we're gonna use the ICS-15 bias exponent. So 5 right here, we're gonna add to 15, and then we get 20. So 20 gonna be represented in the binary string right here. So that's gonna be put into the exponent part of the model. The sign gonna be equal to 1 because the number has a negative. So that's gonna be 1. And the remaining part right here after the binary point right here, so we're gonna put 1 1 0 1 0 1 0 1. So that's a 1 1 0 1 0 1 0 1. Okay, so that the floating point representation of the number negative 26.625.